Hi everyone, in this section we can talk about infrared spectroscopy. And all of you guys are familiar with this one. This is our electromagnetic spectrum. Okay, and if you look at your electromagnetic spectrum, so this end, which is the high frequency, okay, and on this end you can see low frequency, and then this end you have short wavelength, and towards this end you have long wavelength. Okay, so the high frequency are the more energetic ones, like the cosmic rays, and then you have the gamma rays. Gamma rays can destroy molecules, okay, because it's very high energy. And then the X-rays, X-rays can break bonds. Again, X-rays can break bonds, high energy. Gamma rays and X-rays are being used in radiation for the cancer patients because it can kill those cells, very high energy. And then we have UV, ultraviolet light, and under UV also we have UVA, UVB, and UVC. Okay, there are three rays. Ultraviolet light, again, it has higher energy, high frequency, short wavelength, and then the visible light is going from 400 nanometers to 750 nanometers. That's the visible region. So going from VIBGYOR, VIBGYOR, or ROIGB from the other side, violet, indigo, blue, green, yellow, orange, red. Okay, red is towards the 750, and violet is right before ultraviolet. So you can even remember the how the energy separated. So this is violet, indigo, blue, green, yellow, orange, red. So you guys had learned it the opposite way, Roy G. Biv. Why not start practicing it like VIBGYOR, right? Yeah. So right after red you have infrared, and right before violet you have ultraviolet, okay, UV. So that is our visible region. And then right after visible light we have infrared radiation, IR, and then we have microwaves, and then you have the radio waves. So remember we studied NMR, nuclear magnetic resonance, under the radio waves. Now for the IR, going to be in this infrared radiation area. Okay, the greater the energy, greater the frequency. Remember this equation when you were little, when you were taking general chemistry 1. Some of you are still little, right? We never want to grow up. Anyways, so E equals h nu. Remember this equation, energy equals h is the Planck constant, and nu here is the frequency. Okay, so remember we have this equation. Remember we also had this equation that we had seen. There is a reciprocal relationship between the wavelength and, you see here there is a reciprocal inverse relationship between the frequency and the wavelength. Higher the frequency, shorter the wavelength. So the frequency is given in the symbol nu, wavelength is given the symbol lambda. So the frequency and the wavelength has an inverse relationship. That is, frequency is inversely proportional to the wavelength. Higher the frequency, shorter the wavelength. And then if you want to make it a constant, or you want to make that equal, so then we said lambda times nu equals a constant. And then what is that constant? That is the speed of light. So C equals lambda times nu. Okay, and then you can say, if you rearrange this equation, then the nu would be C over lambda. So the frequency can be expressed as C over lambda. And then the energy equation is as higher the frequency, energy would be higher. And then the constant for that is called the Planck constant H. Remember H is 6.34, I believe, 6.234 into 10 to the negative 34 joules second is the Planck constant times nu. So if you put the nu instead of nu, you can use C over lambda. So the energy would be Hc over lambda. Okay. Now for the infrared, we use the wave number. So nu equals C over lambda. So this 1 over lambda equals the frequency. But in IR, we're gonna call it as a wave number. Wave number is 1 over lambda. Okay, that is what we're going to be using in IR. So this is the wavelength. Remember, you know how to find out the wavelength or what is wavelength is. So this is a wave, and we call this as the wave crest, and these are troughs. And then the wavelength is going from one crest to another crest, or one trough to another trough. And then the frequency is how many times the waves passes per second. Okay, how many cycles per second. So the wave number, the number of waves in 1 centimeter. If you take 1 centimeter, how many number of waves? So that is called the wave number. That is how we going to put the peaks in the IR spectrum as a wave number. And one thing that you need to remember here, as the frequency increases, energy increases. Okay, higher frequency means it needs more energy, or a bond carry more energy, meaning that has a higher frequency. Okay, it absorbs at a higher wave number. Okay, a stretching vibration. Now, all we have bonds in the molecules. So this is the hydrogen chlorine bond. What do we have in a bond? We have 2 electrons, right? So this bond can be considered as a spring like that. So it can stretch. It can stretch to either side like that, to this side hydrogen and then chlorine to the other side. We call, if it is vibrate like that, that's a stretching vibration. These bonds always vibrate, and this is a stretching vibration. A stretching vibration occurs along the line of the bond. Okay, along the line of the bond we can see a stretching vibration. And not only stretching, we can also observe bending vibrations when you have 3 or more atoms. Now this one had only 2 atoms, only stretching, but when you have 3 or more atoms, you can observe stretching and bending both. Now these are stretching vibration modes. Symmetric stretch would be the 2 bonds would stretch like this. Asymmetric stretch would be hydrogen-carbon bond would stretch along this way, and this carbon-hydrogen bond would stretch along this way. That's an asymmetric stretch. And then these are the type of bending vibrations. So there are 2 hydrogens, it can bend, not along the bond, but it can bend like that. That's a symmetric in-plane bend. We call it as a scissor. And then you can have asymmetric in-plane bend. That's a rock. This goes to this side, and this also goes to the same side. And this is symmetric out of plane bend. This goes to this way, the other one goes to the other way. That's a symmetric out of plane bend. And you know what's next? Asymmetric out of plane bend, that's called a wag. Scissor, rock, twist, wag. Okay, so those are bending. But normally stretching needs more energy compared to a bending vibration. So stretching would appear their peaks at a higher energy or a higher frequency region. Now each of these stretching and bending vibration occurs at a characteristic wave number. Okay, so carbon oxygen stretching wave. So since it's a inverse 1 over lambda, we call it as a nu bar, which is the wave number that appear at 1700. Carbon oxygen bond stretching frequency appear at 1700 per centimeter. So this is how the IR spectrum looks like. You may have already seen this from your organic chemistry 1 when we did IR for some of your compounds. Yes, we did. So carbon oxygen bond is 1700. You see here, that is wave number around 1700. And then the OH stretching peak appears around 3400, somewhere here, and it is a broad peak due to the hydrogen bonding. We'll talk about it later in more detail of that. So this is how IR spectrum looks like. Okay. Now you can have two distinct areas in a IR spectrum. The two distinct areas, the one is called the functional group region, that appears 4000 to 1400. Normally we start drawing or start having the IR spectrum ranging from 600 to 4000. Now in this range, 1400, from here to 4000, normally we call it as a functional group region. Most of the functional group that we find in organic chemistry, it appears in this region. Now for example, this is 2 pentanol, and this is 3 pentanol. Both of them are alcohol, and the functional group that we have is the alcohol. So alcohol peak is broader peak around 3400. So you have that, and then alcohol peak right there. Okay, and then from 600 to 1400, we call that as the fingerprint region. The functional group may have similar functional groups, but if you look at the fingerprint region for the 2 pentanol and 3 pentanol, are they identical? These two, are they identical? No, right? So this spectrum does not have this bigger peak right there. Okay, but they are not identical. That means this would only be identical to another 2 pentanol. This would only be identical to another 3 pentanol. Normally, if you want to identify a compound from IR, we need to know the IR spectrum of a known compound. And then once you get the IR spectrum for the compound that you are interested, you're going to match the fingerprint region. Even though you know that you have alcohol group, to figure out that is the exact molecule, you have to look up the literature value or the literature IR for the fingerprint region of the known molecule. If they are equal, then we know for sure that is the compound that we are interested. Okay, that's why we call that as the fingerprint region. Just like your fingerprint, you are unique, you have your own identity with your fingerprint. Okay, so basically infrared spectrum alone will not help us to deduce a structure. It will only give us some important information as to what are the functional groups present. Okay, and also if you are doing a reaction that you want to remove a water molecule, just like we did for our methyl cyclohexanol. To begin with, you had an alcohol group, and then when the dehydration occurs, alcohol group disappear. So then your product should not have alcohol group like that. Okay, but it will not tell us what is the structure. It would tell us that our reaction has gone to completion and it was a success. Okay, and these are some of the IR stretching frequencies. Nitrile group carbon nitrogen comes around 2260 to 2220. You don't have to remember any of these numbers. We can always refer to the numbers in a table like this. And also it tells us the intensity of the peaks. Now the intensity depend on how polar the bond is. You see, we have carbon nitrogen, it's a medium intensity. Carbon carbon triple bond, medium to weak. Carbon carbon double bond, medium. Carbon nitrogen, medium. And then benzene, carbon oxygen double bond, carbon oxygen single bond. Now carbon oxygen, there's going to be more electronegativity, going to be between, the difference in electronegativity would be more between carbon and oxygen compared to carbon nitrogen or carbon carbon. So you can see strong bonds. So the polar the bond, it would be more intense. And look at a hydroxy OH group, alcohol. There is a electronegativity between the oxygen and hydrogen, and it is a polar bond. The more polar the bond, you will see a strong intense peak, and in OH that's going to be broad due to the hydrogen bonding. And then for the carboxylic acid, again OH comes around 3300 to 2500. Alcohol also 3650 to 3200. They are strong, very broad peaks. And then the nitrogen hydrogen comes around 3500 to 3300. Medium broad, carbon hydrogen medium. Okay, so the intensity is depending on the polarity of the bond. The more polar the bond, more intense the absorption. That's what I told you, right? Relative bond polarities, relative intensities of IR absorption. So between OH, NH and carbon hydrogen, all of these atoms has hydrogen attached to it, and oxygen is more towards fluorine. Remember, fluorine is the most electronegative element, and then the oxygen, right? Fluorine is 4 and then oxygen is 3.5. So between oxygen and hydrogen we have the most polar, most intense peak. And then the nitrogen hydrogen, the least polar, carbon to hydrogen, least intense. In fact, carbon hydrogen bond is non-polar. Remember, the difference is 0.4. Carbon is 2.5, hydrogen 2.1. So 0.4, between 0 to 0.4 is non-polar. And then above 0.4 to 1.8, I believe, a polar covalent. And then if it is more than 3.8, ionic bond. That's the electronegativity values difference. The greater the change in dipole moment, the more intense the absorption. So the more polar the bond, it can change its dipole moment. So then we will have an intense absorption. You will have one homework question that it's asking you what makes a peak intense. Now you know the answer. The more polar the bond, right? Yeah. And then we also have different masses of atoms. Now, lighter atoms show absorption bands at larger wave numbers. So you have all of these are carbon. Hydrogen attached to carbon. What's the mass of hydrogen? Molar mass of hydrogen? 1.008. And then D. What is D? D is your deuterium. Deuterium is an isotope of hydrogen where it has a 1 proton and 1 neutron. So the mass is about 2. Okay. And then the oxygen. Oxygen mass is 16. Right? And then the chlorine 35.45. So the mass increases. As the mass increases, what happened to its absorption? It comes at a lower wave numbers. But the lighter atoms show absorption bands at a larger wave numbers, meaning the lighter atoms need more energy for it to vibrate, stretching vibration, because they are more strongly held with each other. And as the mass become bigger, so the atomic distance, internuclear bond distance, become longer. Okay, electron cloud is going to be more longer, so it would be easy for these to stretch. If it is easy to stretch, meaning it would need less energy and less frequency, which is your wave numbers. And then you have smaller atoms, they are tightly bound with each other. To stretch them, you need more energy, so then higher frequencies or the wave numbers. Okay. And then look at the bond order. The greater the bond order, the larger the wave number. Bond order tells us about how many bonds are between two atoms. So this is a triple bond, double bond, single bond between carbon and nitrogen. Which one is stronger between the triple, double and the single? It's a triple bond, right? There it's like you have 3 ropes between carbon and nitrogen. 2 ropes, 1 rope. It's difficult to break if there are 3 ropes bound together. So this is more stronger bond. Okay, so that show absorption at larger wave numbers, meaning we need more energy to stretch these bonds, meaning higher frequency, meaning higher wave numbers. Okay, it's not wavelength, remember it's a reciprocal 1 over lambda, so that higher energy, higher frequency. So 2200 per centimeter, and this would be 1600, and this would be 1100, around this region. Just get the pattern or the trend. Okay, again, you don't have to remember the values, but get the trend. What is the trend? Okay, I think I talked too much about this section. We'll stop here and then I'll start this section next.